coherence. All right, so this is, I think, the fourth class on paper. And last time we talked and derived some of these important equations. The next two classes, we're going to look at some sort of physical characterizations that we'll have to remember through the semester, and also derive eventually log law of the wall. And later in the course, we'll do it with compressible flows. And also we'll look at the basics of Kolmogorov theory. But today might be a little bit lighter, and we left off here on the turbulence intensity. So there's really two types of scales we talk about in turbulent flows besides intermediate scales. We'll talk about Taylor length scale today. But of course, the first set is Kolmogorov scales named after Andrei Kolmogorov, right here. And generally, these are just the smallest scales of turbulence. And so that might be the size, the length and time, or even velocities of the tiniest little eddies in a turbulent flow. And we don't call the largest scales largest at all. We actually call them integral scales. And there will be length scales, time scales, etc., maybe velocity scales of the largest structures. And those are easier to estimate because it's usually what you can just see with your eye, and you usually pick a length scale, like the chord of an airfoil, the diameter of the jet, to kind of like just do a crude estimate. And there's better ways to do this that are more mathematical. And somehow we can estimate these or calculate them if we have the full velocity fields. So we still need to introduce a few other concepts before we get there, but one is the specific normal Reynolds stress components. And last time we did introduce the Reynolds stress. Remember UI, uj, bar, and if we set I equals to j, then we would get these terms like ui prime bar. And that's the first one, and these are nothing but the trace of the Reynolds stress. And so these are important components, and we'll see in a second if you take the trace, you'll just get the total turbulent kinetic energy. So the total turbulent kinetic energy from the Reynolds stress is this quantity right, which I wrote right here. If you add up these three fluctuations, which I'll define in a second. And often people, if they're doing hot wire measurements or things in wind tunnels, will normalize these. And that's what I've written here. These Reynolds stresses are often normalized with respect to the mean flow. So if your aircraft is flying at, say, U sub E, or some external part of the boundary layer, that would be one like integral scale of velocity. And there's no real integral scale of velocity in self-similar flow. You could say it's just the distance from the wall at some point downstream, but then that'd be a non-dimensional number. That's why it's self-similar. So if we take each component of the Reynolds stress, or just take each fluctuating quantity u, v, and w, and we square it, and then we take the mean, and then take the square root, you get the same dimensions, right? You'll get a meter squared per second squared upstairs. And downstairs, of course, we have meter squared per second squared, and that's a non-dimensional number. So these can be easily found if you have, right, any three velocity components in a turbulent flow. And you might call these sometimes in the literature relative intensities. Sometimes, and I'll talk about in a second, if you have these, you can characterize wind tunnel flows, like what's the turbulence background level in a wind tunnel. Well, that's done a little bit more informally, which we'll show in a second. So let's look at figure 1.6, and I think mine is upstairs, yours might be down below. But this I have written and taken from a paper by Klebanov, 1955. And this is for a turbulent boundary layer flow. So there's a wall, right? And you have a flow, and there's turbulence in it like this. And then there's the outer edge, which is UE. And in here's all these turbulent structures. And then this is the distance from the wall in this direction. So this is Y. And so that's that. And then this delta is the boundary layer thickness. And the y-axis are these three quantities, which I just mentioned. And they've taken measurements and plotted them. And you can see here that the strongest one is the square root, or the RMS velocity component in the x direction of the flow. That's the direction in the boundary layer, is much stronger than all the other components of V and W. And then this graph here, you can see very close to the wall, y over delta. You're just going from 0 to 0.01 to 0.02. Well, this is the whole graph, right? This is the boundary layer thickness here, which is like delta approximately. You can see very, very close to the wall, the value is even larger. So you're looking at, approximately 12% RMS velocity component. And they're not equal at all. And that's a huge problem when your trace or your Reynolds stress are not equal. That means the statistics are not only varying in space, it's an inhomogeneous flow, but also that it's anisotropic. And anisotropic means that if I rotate a coordinate system in a point in the flow, that the statistics are different. And so this is real measurement, and unfortunately, it's not good news for turbulence modeling, because you may not be able to predict all that, and it obviously could be important. So we could say these stresses, if you will, or turbulent intensities, are different in most engineering flows, and that includes the boundary layer. And it's also showing that it's anisotropic, which I just mentioned that the statistics are different with rotation. So if I rotated my coordinate system 90 degrees, say the U statistics would be different than the V statistics. And typically this is a Klebanov outcome, that he looked at a lot of different low speed incompressible turbulent boundary layers, and he found this ratio, which is pretty famous today. It's the 4:2:3 ratio. And that's just basically the ratio of the maximum intensities in low-speed turbulent boundary layers, but there's no pressure gradients, there's no curvature, it's rather low speed, and this, of course, breaks down when you change any of those properties. So you can't really use this as a modeling property unless your model is just for this basic incompressible flow. So it's not universal, it's just a general rule of thumb for those types of flows. Okay. So you'll see that generally in these streamwise intensities, say U hat goes as about the square root of what U prime squared bar over UE, which is the free stream velocity, and that's usually in the order of 10% for this low speed flow. And especially when these intensities are very close to the surface of the boundary layer. The problem is, for a lot of higher speed flows or just general engineering flows, you'll see that these fluctuating quantities are a lot larger. And so some of these assumptions of turbulence modeling to solve for these flows quickly really breaks down rather fast, but you'll see that we find pretty good predictions regardless. Okay, another thing we might do is we'll sum the Reynolds stress. And this is where we define a really important quantity, which is going to come up a lot in all these models, is the Reynolds stresses. We're going to take the three components, and we're going to define it as the turbulent kinetic energy, and that's called K right there. And so here's the three components of the trace of the Reynolds stress. We multiply it by 1/2, and we can write that more compactly here. And remember, if we have two i's in a term, we sum them from 1 to 3. So that's a nice way to remember it. So UI prime bar is the correlation times 1/2, and that's our definition of the turbulent kinetic energy. Remember, that's the energy associated with the fluctuating motions. And a lot of these models are going to seek to try and predict K. Another great thing about trying to predict K is something that's usually we can try and approximate and measure with experimental techniques. So it's a wonderful quantity because we can directly try and compare K from a CFD code to an experiment and validate our model. Because if we can't predict K and know how much turbulence the energy of the turbulence at different spatial positions in the flow is, then the model's not very good. It's not predictive. So it's also a per unit mass basis. So it's consistent with a lot of the Navier-Stokes analysis. And you'll see that, unfortunately, if you do make this approximation, you really have no idea in a turbulence model that the flow, like the different ratios of the trace tensor, of the Reynolds stress tensor. So most practical models predict K, but don't predict individual components. And that's okay. So what does that mean? In terms of the model, you'll just say U prime bar is approximately squared equals to V prime bar squared is approximately equal to W prime squared bar. And you have no other real choice if you solve like a standard 2-equation model or even 1-equation model. You have no other insight into that. If you do make this assumption, you could also put on the additional constraint that the turbulence is isotropic, meaning that all the statistics are the same with rotation. And that's kind of what this is saying, and that's also saying that's true for off-diagonal terms. And then we can define this sort of turbulence intensity in terms of percent. And when you go into a wind tunnel, you might ask, hey, what's the incoming sort of turbulence intensity? And they'll give you this number. So what they'll do is they'll try and measure K with a probe in the tunnel for different speeds. And then they'll divide it by the incoming speed in the inlet of the tunnel, square it, multiply by 2/3, square root, and multiply by 100 to make it a percent. So, typical tunnels might have a few percent turbulence intensity in the incoming flow, which you may not want if you're flying out in the atmosphere in a low turbulence environment. And really good low turbulence tunnels might have something on the order, really good, 0.5% turbulence intensity. I would consider that a good low intensity wind tunnel. Okay. So we'll put that there. And what we haven't really talked about, I believe, is really 2-point correlations. We talked about 1-point correlation previously. And you might wonder why we are looking at 2-point correlations in turbulent flows. And that's really mentioned by Townsend in a second, and we'll read this together. But first, for these like large-scale turbulent structures, that's a horrible turbulent structure, but these large length scales, we might say that the largest scales have long lives in terms of time and space. And they can't really be described by 1-point statistics, unfortunately. For example, if there's a large-scale turbulent structure and I can only get a measurement at 1 point, how can I ascertain how long or large it is, right? So if this is a big piece of turbulence and I only have a point and a measurement, it's very hard to describe it. I would need at least 2 points. And it can be shown in 2-point statistics. If I take measurements at 2 points, then I can always add more points and relate one statistic to another. So there's no point in doing 3-point measurements because you can just do a bunch of 2-point measurements. So here's an interesting quote by one Townsend, who's well known in the field. And he wrote, unlike the molecular motion of gases, the motion at any point in turbulent flow affects the motion at other distant points through the pressure field. And an adequate description cannot be obtained by considering only mean values associated with single fluid particles. This might be put by saying that the turbulent motion is less random and more organized than molecular motion. And I'll pause there because that's an interesting point. When you think about the kinetic theory of gases, you have a bunch of particles and they're all seemingly moving around like billiard balls on a pool table. There's some order to that. But he's saying that the large-scale turbulent structures, at least, are more predictable and less random than the molecular motion at the atomic scale. And he's saying that to describe the organization of the flow will require mean values of the functions of the flow variables for 2 or more particles at 2 or more positions. And this is the key point at 2 or more positions. And so this paper in 76 was also making some of the same arguments, a little more mathematically and experimental data than I am right now in the class. So when we look at 2-point correlations, they'll be important because we can derive and look at how we might calculate with like a 2-point measurement in a turbulent flow, the large-scale turbulent structures. And there's really 2 kinds of 2-point correlations, and they're related to time and length scales. And you might imagine we might do these correlations, right, in time or space or both. And so if we have a little coordinate system, we might say here's x1 and here's x2, and this is the locations where I might take measurements and find out something in between them. Right, when we were talking about 1-point measurements, I've always asked, like, hey, we might find an autocorrelation or a correlation between 2 quantities like UI, and they're located at the same positions. In this case, I have 2 different points and 2 different measurements, so it's separated by some space with a vector, say r, and I don't even have to be measuring the same quantity. For example, one probe might be measuring temperature, and another probe might be measuring velocity. But for now, we'll just say we're going to look at 2 velocity components in a turbulent flow. And Taylor envisioned all this in 1935 and said, well, this might all be related by this equation. And what is this equation? Well, it's a partial t goes as negative u of partial x. So this is the partial derivative with respect to time. And this is a partial derivative with respect to space. And so what is this factor? It's negative u, where u is a convective velocity. And that's the speed at which turbulence moves through space. And unfortunately, it is an approximation because measurements show that the convective velocity of turbulence sometimes is not equal to the average velocity of the flow. For example, this tripped me up and almost lost my Ph.D. dissertation, is an experimentalist, and I made this approximation that the turbulent structures are moving at the mean flow speed. He said, well, measurements show that in a jet flow, they move at different speeds depending on the radial location of your turbulent jet. And so a lot of people say, oh, the turbulent convection speed is like 70% in a jet is a first order approximation. And the higher order approximations, you can say it varies with position. It could vary between 40 and 70%. Or you can even do it on like a wave number basis and show that different scales of turbulence are convecting in the flow at different speeds. So this is kind of like your 0 order approximation. It works really well. And here I wrote the bottom line, what the equation means. It implies that the turbulent fluctuations are convecting at the speed of the mean flow. And it's really valid or very, very good approximation for fluctuations which are weak. So if your turbulent fluctuations are on the order of 1% to 5%, in that range, this works really well. For highly intense turbulence, Taylor's hypothesis is unfortunately going to break down. And the good thing is, it means that 1-point statistics can be related to 2 points in practice through Taylor's hypothesis. So let's look at one example. And this is really a 1 spatial point correlation, but at 2 different times. And this is what we call the autocorrelation tensor. And so if you're in a wind tunnel and doing turbulent measurements, or wherever in the atmosphere doing turbulent measurements, or underwater, you can always take a 1-point statistic and look at the correlation essentially at different times. So you can see here we say maybe UI, that's Reynolds stress term, UI uj prime. And instead of just saying, oh, it's, you know, at just one point, well, it is at one point, but now we are doing it at two different times. And this is maybe a more rigorous way to define turbulent kinetic energy. So you see here's the turbulent kinetic energy term, and it's nothing but the trace of the autocorrelation tensor times a half. And so this is exactly consistent with our earlier definition of TKE, turbulent kinetic energy. But you'll notice that in this equation, T prime is obviously set to 0, and it turns out that K is a function of space and time. And you would expect that, right? So if any point in the turbulent flow at any time, I would expect the amount of energy in the turbulent fluctuations to be changing. I mean, great examples would be just like in this room, if we closed the door and all waved our hands around a bit and just stopped, we would have created a bunch of turbulence. It would fill up the room and decay. And at any point in the room, we could measure K and watch it decay. And that's exactly what kind of like a homogeneous isotropic turbulence would be. Okay, with that, we might also try and define larger time scales. And what we would do is integrate R over all possible values of T prime. So this function, right, it's at a particular spatial location, and we integrate over time. Say dt prime, we'll integrate that away and divide by 2k, and then we'll get to dimensions of seconds, right? So this is meters squared per second squared. This is meters squared per second squared. We're integrating in time, so our units are seconds. I always like to check the dimensions of this equation. It does turn out to be, this is an integral time scale from an autocorrelation measurement, single point measurement. But the definition came from 2 point by setting x1 equals x2. That's where it comes from. So this is an important definition because it indicates like the lifetime of your largest scales of turbulence. So you might say, okay, if I have this large scale of turbulence, how long does it last? That's how we would talk about it. We'd say that's the integral time scale, the largest scale. Okay. I might also say that this can be simplified because like in wind tunnel tests or experiments in practice, you don't always have all the components of the trace of, say, this autocorrelation. So you might just approximate R11 of x and t prime as u prime of xt, u prime of xt plus tau prime, and then do the integral. And that's a much more practical way of doing it. So if I just have a hot wire, I'm getting one component of velocity, and I perform the operation, and then I can define and approximate the integral time scale that way. Good. So let's look at our next equation. And if we normalize this form by u prime squared, the RMS velocity, we'll get what we call the Eulerian time correlation coefficient. So let's talk about some properties, and we'll show a graph of this in figure 1.7 in a second. You'll notice that if I set t equals 0, t prime equals 0, then of course RE equals 1. And for large values of t prime, then RE will go to 0. And if I have large negative values of t prime, it will go to 0 too. And it turns out in turbulent flows, it's also symmetric about, of course, t prime equals 0. So let's look at one typical plot of this, and this will be in figure 1.7, I believe, way down here. And so here, here's what it looks like, and it's this particular line here, right there. And you'll notice something interesting about this. A lot of people approximate these functions for theoretical considerations as Gaussian functions, because they might say, oh, this looks a lot like, you know, a Gaussian function that looks like this. And it's a very good approximation, but Gaussian functions are always positive. right? They have no negative loops. When people talk about negative loops and turbulence measurements, they're talking about these little things that go up and down around the x-axis. Those are the negative loops. And I think some of my students and people in aeroacoustics have often approximated these functions because that's how they estimate acoustic sources in turbulent flows. So that's very typical, and that's what you should see if you normally take measurements in wind tunnels or if you're doing some kind of modeling. Okay. Now let's just say we take that same function RE and do a Taylor expansion about t prime is 0, and you can write it after truncating higher order terms as this function. So that's 1 minus t prime normalized by tau e squared. So that looks like some parabola, and that's what's plotted as the dashed line here in figure 1.7. And that's an interesting plot. And it intersects the x-axis at some t prime here and here. So this distance from the y-axis to this location is tau e. And that's what we call the microscale, tau e. And you might say, why is that important? Well, it depends on what you're doing. For turbulence modeling, may not be that important, but it's seen as an intermediate time scale between the largest scales of turbulence and the smallest scales of turbulence, which are the Kolmogorov scales. So that's like a geometric interpretation of that. And I've kind of made the notes in this section verbally, but you just say tau e is intersection of parabola of figure 1.7, which of course is the autocorrelation. And most importantly, tau e is an intermediate time scale. Okay. So let's look at now a two-point correlation. Maybe I didn't let everybody write that down. People catch up. So now we're going to look at the more general two-point correlation. I'm going to kind of move a little bit faster through some of this because it's more straightforward. We have Rij, we take the correlation, and now we have T, and now we have X plus RT. So you see T is the same in the argument between Ui and Uj, and X is separated by that vector R, which I showed earlier. So we have, say, X1, X2, and there's some vector R between them. And so really the two-point correlation is defined as like any 2 points in like your turbulent field separated by a vector R. And we can choose to put these points anywhere we want, but it certainly makes a lot of sense to put them in, say, the same turbulent eddy if we can. Otherwise, they'd be totally uncorrelated. Once again, you can recover, didn't want to do that, recover turbulent kinetic energy by setting x1 equals x2 and leave time there and set t or tau prime if there was one. Really, this is, you can make it more general by writing t plus t prime there. Then you have a two-point space-time cross correlation. You can recover turbulent kinetic energy. So what if we take this equation, the two-point correlation, and set it to RII and let this form go into the numerator of this equation and integrate over all distances and normalize it by turbulent kinetic energy. And then in the numerator, I'll once again have meter squared per second squared all over meter squared per second squared. And I'm integrating with R, so that's a units of meters. You can see I'll find a length scale. And 3/16 is by convention. And this represents the integral scale of turbulence. So I could go into a wind tunnel, and I can make two-point measurements, and I can find the time scale and integral scale of turbulence in my entire flow, just through two measurements. and they represent the largest scales of turbulence in time and space. And I could also estimate a velocity, integral velocity scale just by taking the ratio. No problem. There's also something called a Taylor microscale, which is an analog to the intermediate time scale. And so how about I just define F here? And this is called a longitudinal correlation function for stationary turbulence. So we define that. And it's nothing but R11, which is just the first component of RII, divided by the RMS velocity. So see, in this equation, we have the whole trace of the Reynolds stress tensor. In this one, we just have the first component, the 1,1 component. And so you can see the dimensions of this should, of course, be, well, nothing really. It's dimensionless. And we'll try and construct a parabola for F, just like we did up here for the intermediate time scale. So we have one for space. And using Taylor's hypothesis, which was up in equation, I'm going to go way up here. What equation was that? 1.50. So we'll mention that equation. I should have put it in the notes. You can show that the Taylor microscale goes, which is lambda, goes as some velocity scale, like the velocity of the flow, that's that convective velocity times that intermediate time scale. So that's a length scale. And so if we plot the scales in terms of energy in a turbulent flow, first wave number kappa, you should see something like this. Here's the integral scales. And we'll look at this in more detail on Tuesday, excuse me. And here's the smallest scales. This is the location of where Taylor's scales are, the intermediate scales. And usually this is a logarithmic plot, so it's really log of kappa. And there might be many decades or orders of magnitude between the largest scales and the small scales, and we'll try to estimate that. Now let's say we just say, oh, the turbulent field is homogeneous and isotropic. Taylor also showed that the turbulent kinetic energy decays as -10 times the viscosity times turbulent kinetic energy divided by the Taylor microscale. So this is one useful thing in turbulence modeling you'll see, is that when we have to close the turbulent coefficients and create models, we actually have to sometimes turn to statistical theory or experiments to calibrate them. And the decay of homogeneous isotropic turbulence is one set of way to find those coefficients. And we'll look at that and refer back to this later in the semester when we look at industrial turbulence models. So what does this mean? It means that the energy in the turbulent field is obviously decaying. There's no production. There's nothing creating turbulence. So if we were in the room and mixed up the air and just waited, it would eventually become homogeneous and isotropic, and it would decay according to this law. Now, if that's true, all the energy is dissipating at the rate of decay of turbulence. So remember in the last class, we derived an equation, a huge equation for epsilon. But if we make the assumption that we have isotropy and the turbulence is homogeneous, then this equation holds. It's like an energy equation, but it's an energy equation for the energy of the flow is dissipating. Anyway, we'll set epsilon to 10 nu kinematic viscosity times turbulent kinetic energy divided by the Taylor microscale. What do we get? Well, if we have a large Reynolds number, very large, like millions or preferably larger, then in the same paper, Taylor shows that the dissipation goes as k to the 3/2 over the integral scale. This is just dimensional argument. That's all it is. He just knows the dimensions of dissipation, dimensions of turbulent kinetic energy, and divides by the length scale, so you get the dimensions of epsilon. And it so happened that it works well when comparing with experiments. And so that's a powerful tool, which we might look for in the future. And it's not really estimating the small scales of turbulence yet, but kind of fitting in a few parameters. This was based on dimensional analysis. By fitting a coefficient, it corresponded really well with measurement data, and that coefficient was 0.09. We'll see later that Andrei Kolmogorov in the Soviet Union showed that the smallest scales of turbulence are dependent only on the viscosity and the dissipation in a flow. So that's interesting. It has nothing to do with the geometry, has nothing to do with the amount of turbulent kinetic energy in there. The smallest scales of turbulence go as the viscosity cube divided by the dissipation rate to the 1/4 power. And we'll show that on review Kolmogorov's theory on first thing on Monday. And so what Taylor did here is he related these microscales with, excuse me, let me get my right page of notes out here, with lambda. So this is the Taylor microscale. This is Kolmogorov's scale, which is small scale of turbulence, and it goes as the ratio of integral scale divided by Kolmogorov scale to the 1/3 power. So that's the largest scale turbulence divided by the smallest scale turbulence to the 1/3 times about 7, which is an empirical coefficient, goes as Taylor microscale divided by eta. And so that's a nice thing, but it won't be extremely useful in turbulence modeling, but it's good to have like intermediate scales. And I hope you see why later in the course. Okay, let's go down here. And some people call the Taylor microscale a hybrid length scale because it's not the largest scale of turbulence, and it's not the smallest. And this is the final equation on micro or intermediate scales I want to show. So this is just a length scale which involves quantity, which could be large and for energy-bearing eddies, and it also involves like characteristics of the dissipation and viscosity. I'm going to leave that there for now, because I only have another 10 minutes. So I want to get to some more general properties of turbulence. Okay. So a lot of people have a lot of trouble defining turbulence, and even people in the field who I've been working at for decades, I see in conferences argue about what those definitions are. I want to just try and talk about that a little bit before Monday's lecture on the boundary layer composite profiles and Kolmogorov's theory. So G.I. Taylor, he wrote that turbulence is an irregular motion, which in general makes an appearance in fluids, gases, or liquids, when they flow past solid surfaces, or even when neighboring streams of the same fluid flow past or over one another. And I think this definition has been argued about a lot, especially because it uses the words irregular motion. That might be a better definition just for kinematic theory of gases, because it's shown by multiple people, for example, Brown and Roshko at Caltech, Molo Christensen at MIT in the 60s, that these large-scale structures have strong coherence and length scales, and they're not irregular or truly chaotic either. So this bugged people. Another thing that is maybe not aligned in this definition is that they have a very strong dependency on initial conditions of the flow or boundary conditions. And so that's really where the first computer project is coming in, the high sensitivity of turbulent flow to small perturbations, very small perturbations. So another good definition, I think, in the community came out by Heinz in 1975. I'll read this one to you. And he wrote, and I quote, "Turbulent fluid motion is an irregular condition of flow in which the various quantities show a random variation with time and space, so that statistically distinct averages can be discerned." And probably a good part of this definition is that it's more complete. And Cebeci-Smith modified it a little bit, that turbulence involves a wide range of scales. And you can see that just from Taylor's analysis from 1935, that there's going to be huge scales, like in the atmosphere. They might be on the order of kilometers, and the smallest scales might be on the order of centimeters or even smaller. And that's a huge range of decades. I note that the turbulence might be represented by frequencies and wavelengths, and that's why Fourier series and Fourier transforms are going to be so important in this work, because that way we can decompose the space-time field into like a wave number field and say, okay, well, certain sizes of turbulence have certain energies. And that can all be done mathematically. In the interest of time, I'm going to come down here to making some notes about where this turbulence is coming from. The first is on instability and nonlinearity. And when we look at the Navier-Stokes equations, even if we have a laminar flow, there's a nonlinear term in the momentum equation and that nonlinear term causes the flow to be unstable due to any small perturbation. So of course we have nonlinear equations, and instability will lead to turbulence, which isn't good, or could be good depending on your point of view. If we do like a linearization, like to do a stability analysis, you might look at linear stability theory. You're really throwing away the nonlinearities of the flow. So you can predict the transition and stability of the flow, but you can't predict the chaotic motion that occurs afterwards. So linearizing the equations can eliminate the turbulence. Oops. Which is okay, but it's not a good model at all. So you do have to keep nonlinear terms. Absolutely, it's time-dependent phenomena. You can't have turbulence without time dependence, and you can't have it without 3 dimensions. And that's because there's vortex stretching, and it's highly time-dependent, as you know from the partial t terms in all the equations. It might be seen as random fluctuations, but it's not like random like in rolling dice. It's truly deterministic. And by deterministic, I mean it's predictable, that if you know everything at one point in time and space, then in theory or technically you should be able to predict everything else in the future. And if you don't believe that, then you should just quit now and not use the Navier-Stokes equations at all. You'd have to use maybe a stochastic form of the Navier-Stokes equations, or Monte Carlo methods, like build in statistics into the equations. And this is something I've always had an interest with people, because we have a few more minutes, because they would argue that the Navier-Stokes equations as a full set, if they're compressible, are already statistical because you're using the first law of thermodynamics. But the Navier-Stokes equations themselves, the continuity and momentum equation, are deterministic. Another thing that's probably important to remember is it's a continuum phenomena. And what does that mean? Well, let me give it an example. Say we're in a rarefied flow, one where it's not very dense. Maybe we're just starting to re-enter a planet's atmosphere, and the flight vehicle experiences a rarefied flow. So you might say, is the flow around the vehicle turbulent? And people might say no, because you don't have enough particles to form turbulent structures. It's like a Newtonian flow, where every little particle might be modeled and just bounces off the vehicle like billiard balls. There's no chance for instabilities to form. There's no chance for like true shocks to form, because shocks are actually continuous. They're not really discontinuous. like if it's an inviscid flow. And so for turbulent structures and for turbulence to form, it has to be a continual phenomenon. And so that means the Knudsen number, Kn, which I talk about in my compressible flow class, has to be non-rarefied. And of course, there's whole classes on that. And it's also, of course, shown, that the Navier-Stokes equations assume that the fluid's a continuum when you start. So that would break down the definition. This is illustrated in the book by Tennekes and Lemley, which is an amazing introduction to turbulence book for experts. And they wrote even the smallest scales occurring in turbulent flow are ordinary far larger than any molecular length scale. So that means we have the largest scales of turbulence, we have intermediate scales like Taylor's, and then we have the smallest scales of turbulence, which are like Kolmogorov scales. And then even smaller than that are, of course, all the molecular, intermolecular force scales. But in terms of like Navier-Stokes equations, those scales are way smaller than the smallest scales of turbulence. So we wouldn't necessarily worry about them and just treat it with a statistical technique. The smallest scales are many orders of magnitude smaller. The largest scales, and just what I said, the molecular scales are even smaller. And if you want to do a direct numerical simulation of a turbulent flow, you can make easy estimates of how many numerical operations you need to resolve the small scales of turbulence, and it goes as the Reynolds number to the 9/4 power. So usually in the introduction to CFD class, we derive this property. If you're interested in that derivation, I can show it to you, or you can look it up in a paper by Parviv Moin at Stanford Center for Turbulence Research. Just do a Google search for direct numerical simulation, Parviv Moin, and he has a little part of his paper in the annual review of fluid mechanics where he looks at that. Since it's 1:39, I don't want to keep you over class. That's not that polite. But we'll pick up Monday, quickly do vortex stretching, and look at some of these examples, and then get into the cascade theory. Okay? So thanks very much for your time today.